All right. Let's get started. I'll be honest, for a second there, I had to look and go, okay, yeah, this is concrete design, because I know that concrete and steel can bleed together a little bit, even for me. So in here, we don't have a celebration coming up for a little while, so the only thing we have is homework number 4. That's due next Friday, so you got plenty of time on that. You all just turned in homework number 3. That isn't hasn't been graded yet. I'm guessing, I'll be honest, I'm guessing that probably won't be graded until later, like later next week. But I mean, I'll make sure you have the solution and whatnot in time. When it comes to homework number 4, you all will turn that in on Friday, and if I remember the schedule correctly, we have an exam review Monday, and then we have the exam the following Wednesday. So when that homework gets closer, we'll discuss some logistics with that later, but we still got plenty of time on that. The only other thing I'll mention is Engineering Career Day. The event is on Thursday. Now, to be honest, the event isn't really for college students, it's for high school students to try and get them interested in engineering. But the event is organized and hosted by SAME, the Society of American Military Engineers, and they host a youth social the night before every year. So that's Wednesday, February 20th. It's going to start at 5 p.m. It's over at Fat Patty's. They are paying for like food, like they're going to have a bunch of like appetizers there, and there's going to be a lot of like contractors and USAC employees and whatnot. So there's going to be, you know, think about it, there's going to be free food and networking opportunities. So go, you know. It's free food. That should have sold it right then and there for a college student. You kidding me? So yeah. On Thursday, though, is the Engineering Career Day event. I will go ahead and do my pitch right now. It would be nice, just if your schedule's available and if you're interested. There's going to be a lot more employers at Engineering Career Day than there are going to be at the Youth Social. And if you're available, I wouldn't mind coming down for an hour or so to maybe help out. That would be great, and it'd put you in front of some potential employers there as well. So if you're interested, let me know. We can talk between this and steel and whatnot and go through that. Everybody good? All right, so we're going to continue on in beam design mode. Just so everybody's clear, we mentioned this last time, but we're going to do, so we did unknown cross-section design. We're going to do known cross-section design. Then we're going to do slab design. And that's exam 1. So exam 1 stops with slabs. So just so everybody's aware. We probably won't finish slab design today, but we'll at least get, you know, a good bit of the way there. So with that, let me go back a little bit. Let me go here, because I know this is a little bit behind, but I'd like to sort of just recap everything. So, you know, just sort of getting everybody onto the same page and make sure everybody sort of sees where we're at and where we're headed. We started off, you know, this discussion of economy and reinforced concrete beams. When we began that discussion, here, I didn't mean to go back. We began that discussion with the concept of a reinforcement ratio. We started talking about how reinforcement ratios are really, really valuable tools for design mode. And we derived in our, you know, previous lecture, well, we looked at, okay, there's a couple rules of thumb that we can use, like 0.18 FC prime over Fy. There's equations like this, where you can derive a rho to achieve a target strain value. But both of these formulas are really only useful when you have no idea what the beam looks like, okay? So, you know, we went through this, you know, we started laying out our procedures for design. And we started off with unknown cross-sections, so this is when you don't have a clue what the beam looks like at all. And we went through that process, and when we get to our rho value, we're basically just picking a value out of the air, or we're picking a value to achieve a target strain value. But either of those expressions have nothing to do with what the beam looks like, because you don't know what the beam looks like. You're in design mode with an unknown cross-section. So it really doesn't make sense at this point to use a rho value based off the dimensions of the beam if you don't know what the beam looks like. So when we went through this process, the process was a little longer because we had to derive what the beam looks like and go through that and then evaluate it. And so this example took a good bit of time. It was a pretty comprehensive example. So we went through this, and then we had, cover requirements and whatnot, and then we did this example. So pretty straightforward. Anybody have any questions on that example? Okay. Then we said, okay, well, what about a known cross-section? So maybe you're using reusable formwork, you're using precast elements, so you have an idea of what the beam looks like. So now we have the design of a known cross-section. Knowing how to design a known cross-section, even if you're not going to use precast elements, even if you're not going to use reusable formwork, it's still a valid process to be able to, you still need to understand that process, because if you understand how to design a rectangular reinforced concrete beam with a known cross-section, then you know how to design a one-way slab, because the process is very, very, very similar. So even if you're not going to use reusable formwork, this is a valuable exercise. Because we know what the beam looks like, the process is a lot easier and we can get a lot more scientific about it. See, here's our expression for Mn, and remember, all this equation is this is just ASFY d minus A over 2. All that expression is taking ASFY d minus A over 2, plugging in our expression for A, then substituting our expression for rho, and doing a little bit of algebra and arithmetic to make the equation a little prettier. And so this expression will tell you the nominal moment capacity of a beam as a function of the material strengths, the beam's dimensions, and rho, the reinforcement ratio. And that's highly valuable if you're in design mode, because if you don't know what the reinforcement is, all you'd have to do is just take this expression and solve for the reinforcement ratio, and you've got what you need, because that's what we're trying to do. We're trying to determine AS. So AS is rho BD. If you can determine what rho is, you're good to go. So all we do is we take this equation, do a little bit of algebra, alphabet soup, rearrange it a bit until we get it into a form that looks like this. And if you look at it in terms of rho, just take a look at it. It's a pile of junk times rho squared minus a pile of junk times rho plus another pile of junk equals 0. That's the quadratic equation if I've ever seen it, what does the quadratic equation look like? It's a pile of junk times x squared plus a pile of junk times x plus a pile of junk equals 0. So if you look at this, this is basically a quadratic equation in terms of rho. And so by now, everybody knows how to solve a quadratic equation. You did that in high school, or you went through that in algebra or pre-calc or whatnot somewhere here at Marshall. So x equals negative b plus or minus square root of b squared minus 4ac over 2a. Just do that for this expression. So take this, chug out the quadratic formula, do a little bit more alphabet soup to simplify it. This is going to be a lot like what we did for remember when we were trying to determine neutral axes and we had a quadratic equation and we solved it, but we realized that there was only one value that made sense. Remember, we had a neutral axis, there was like a positive value and a negative value, and one of them didn't make any sense. Well, the same thing happens here, and so we get the following expression. Now, I want to be absolutely clear so everybody sees this. This is not a typo. So we have this term in parentheses, and we have 1 minus the square root of 1 minus. That's supposed to be there. There's 2 1 minuses. That's just me factoring that out and making it a little easier to utilize. So just so everybody's aware. We're going to do an example problem here in a second. We're going to use that formula, and I want to make sure that everybody gets the same answer when we do the math. So speaking of the procedure is really simple. In fact, there's really only one assumption, and that's phi. Remember, phi is a function of the strain in the steel. We do still have to make an assumption there because we don't know what the strain in the steel is, because we don't know what the steel looks like. We haven't done a design. So we would assume a phi value of 0.9. First off, we have to compute the factored moments of the beam. The nice thing about that is because we know what the beam looks like, we don't have to assume a beam self-weight. We have the beam. We know what it looks like. So compute an mu, then compute an mn. Then once we have mn, we compute a rho value, and instead of guessing some rho value, we can use this equation because this is solving for rho given all these variables that you know. So it's a little involved, but it's not too terrible. Then AS is rho BD. choose an area of steel pattern that makes sense, and move and analyze and verify your assumptions. And that's it. So it's a pretty straightforward process. So with that, we're going to do this example. I made this example short for a very particular reason. Example 6 was really long, and it was really comprehensive. So for instance, on this example, step 1 is to determine the factored moment. I just gave it to you because we've already done that. We did that like twice on the last example. There's really no point in doing it again because I have a feeling you all know how to do WL squared over 8 by now. So we're going to select the reinforcing steel for this cross-section. So you've already got the beam dimensions. You only need the area of steel. We've got FC prime. We've got FY. So we can just sort of get to work. Everybody good? All right. Now, so we know that B equals 16 inches. We know that's 21 inches. We know FC prime is 3 KSI. While I don't think we are going to use it, that ends up meaning beta 1 is what? So if FC prime is 3 KSI, what's beta 1? No. It's still 0.85. It's 0.85. I can see where you'd say that. But at any time that FC prime is 4 KSI or less, beta 1 is still 0.85. We know that FY is 60 KSI. And so basically what we're trying to find is that we just don't know what the area of steel looks like. So ultimately this is a pretty straightforward process. So it would start out with like a step 1, which is computing the factored moments. And so just to get everybody on the same page, if you go back to the previous example, if I scroll up a bit, that was a long example. But if you go back to the previous example, there was a lot going on there. You know, we had to compute the self-weight, factor the loads, 1.2 dead plus 1.6 live. We did quite a bit to get there, but I made it easy on this example and I just gave it to you. So this is 160. So that's easy. And you'll find me do that a couple times throughout the examples that we do in class. For instance, when we do T-beam design, we're going to have 2 T-beam design examples, and on one of them, we're going to do it from start to finish. But then on the second one, because there's a couple things that are different, and that's really what I want to emphasize, I'm going to give you a lot of values to make that example go a little faster, because I just want to, make it, I just want to streamline it a bit. All right. So I'm going to need your help on this one. Step 2 is to compute required MN. And so MN required is going to be MU over phi. And so in order to do this step, we have to assume what? There we go. Now, that's what we desire, that's what we want, but we have to write that out here because we don't know what the steel looks like. So this is 160 foot kips, which, by the way, here I'm gonna introduce you to something. I think I showed you this a little bit in structural analysis, but if you ever see me do this, if you ever see me go foot kips, that's sort of my shorthand for foot kips. So if I just do like 160 foot kips. So, and that's 0.9. If I divide that out, what is that? I'm going to scroll that down a bit. 177.78. 177.78. Do I have a second on that? Yep. All right. And so that's foot kips. Okay, do me a favor. Since we're going to be plugging this into a pretty large expression here in a second, let's go ahead and do that in inch kips. So multiply that by 12. Tell me what you get. Like that? Do I have a second on that? Okay. All right. Okay, now step 3 is to compute required row. And so row required, this is going to be a long equation. And so we've got 0, I think it's, remind me, it's 0.85 FC prime over Fy. Okay, and then it's 1 minus the square root of 1 minus, and it's a fraction. On the bottom of that fraction is 0.85 FC prime BD squared, and on the top of that fraction it's 2mn, right? Man, that was by memory. Okay. So you can see why I converted that to inch kips, because we're going to have inch kips. That's going to be in KSI and inches, so it makes sense to convert accordingly. Okay. So 0.85, and that's 3 KSI? What? No. All right, so that's 3 KSI, and that's over 60 KSI. And if you wanted, you could use PSI, but just you got to be consistent. Now, I said PSI, and I was thinking that. So that's KSI. I'm going to put that in a bracket, so 1 minus 1 minus. Okay, and so on the bottom, that's 0.85. That's 3 KSI. That's 16 inches. That's 21 inches squared. I got to stretch that out a little bit further. Okay, and that's 2 times 2133.3 inch kips. That looks suspiciously like a multiplication, so decimal. Right. It's going to be small, right? Yeah, that's a good point. Remember, this is a reinforcement ratio, so reinforcement ratios are tiny. They're not like 26. They're 0.00 whatever. They're going to be tiny. So maybe we should be a little exact with this, just to make sure. Like, I probably wouldn't be this exact in practice, but since we're in a classroom setting, make sure. Let's go like 5 decimal places.
0.0053.
Yeah, I might do something like 0.5, like 0054, but let's do that. Okay. Now I'm going to wait a little bit because I'm not going to call for just like seconds. I'm going to call for like thirds, because that's a big equation. That's what you got? You got? Okay. Everybody else getting this? Everybody good? Okay. Okay. All right, so now we can compute our required AS. And so AS required is just going to be row BD. So 0.00538. And then 16, 21. And so what does that come out to be? Say it again. 1.81 square inches. Do I have a second on that? Okay. Okay. So if you're okay with that, what we can do is we can go off of our beam design aid, just as we did before, and we can say, okay, let's find some options that work, and let's compare those options against their minimum beam width, and see if we can find a valid option. So, what did you say? 1.81. 1.81. So, would 17 number 3s make a lot of sense? Not in a single layer, because if we scroll down on the bottom, nowhere near. That's another thing. When in doubt, unless it's otherwise stated, always assume a number 3 stirrup. And if you're wondering why, I want to hold that explanation until we start talking about shear. So unless otherwise stated, always go with this number 3 stirrup. So, okay. Let's start off with the number 5s. So I propose that that's an option. We could go with 6 number 5s. Would 6 number 5s fit in the beam? On the bottom, so we have 6 number 5s. Wait, that's the wrong one. Nope. There we go. I'll have my keyboard hooked up. There you go. So we could go with 6 number 5s because that's enough steel. And would that fit inside the beam? Yeah, that would fit inside the beam, because the beam, what is the beam width? 16 inches. And for 6 number 5s to fit in the beam, we need 13.38 inches. So that would be a valid option. Now I'm curious, really, are there any other valid options? Because let's just go through the areas. So number 6s, the next highest up would be 2.21. No reason to pick that if this works. We've got 1.8, no reason. Yeah, that's going to be it, right? Does everybody see that? So really, that's going to be the most valid option. There is no steel pattern that's bigger than 1.81, smaller than that choice, and would fit. There's none. So really, that's what we're gonna go with. So this one's a lot easier than the last example in terms of picking a pattern. So 5, select pattern. So here's our beam. And we're going to end up going with 1, 2, 3, 4, 5, 6. 6 number 5s. Well, that's a great question. We could, but if we use 2 number 9s, we'd have 2 square inches, right? So between this and this, which uses more steel? This one does. So if you're buying steel per pound, why would you not go with 2 number 9s as opposed to that? It's more expensive. So if there was an option that was like 1.82 or 1.83, I would pick that because it's higher than our required 1.81, but it's less expensive. In the end, that's going to be the cheapest choice. Does that make sense? That's a good question. Now, let me say this. I am living in a world where every single piece of steel has unlimited availability. What if I call the supplier and all they got is number 9s? Well, guess what? I'm going with 2 number 9s. You see what I mean? So, and so here's our beam. And so that is 21 inches. Are we done? Do we have enough ammunition at this point to say that this is our beam? We have to check some things. At the very least, what do we have to check? Say it again? Exact fee. We guessed a fee value, right? So we would have to go back and analyze this beam. Now, I'm going to be honest, I'm not going to do that for this example because if you can do step 9 on the last example, you can do this. It would just be a full-blown analysis example. So here's what I'll do. I'll do this. I'll stay step 6, analyze trial section. And so how did we do that? Like, what was the order? Like, what's the first thing that we computed? Anybody remember from we computed A, then we computed, well, no. We computed MN. Then we computed C. Then we computed epsilon sub T. Then we computed, then based on this, we determined like what was phi, right? Then we said phi MN. And then what's the last thing that we determined? AS min. And so our goals were what? Phi MN had to be greater than or equal to MU, right? We had to determine that epsilon sub T is greater than or equal to what? Somebody over here. 004. We had to determine that AS was greater than or equal to AS min. And there's one other that we had to determine, or what we were trying to determine. We wanted the efficiency to be greater than or equal to what? About 90%. Now, the one thing I'm not including in this step is that normally there's one other thing that we'd have to compute, and that would be MU. Like, we'd have to recalculate MU. We don't have to do that for this problem because it was not just that it was given, but because it's a known cross-section, there's no need to iterate. Remember how this was on the previous example. We made a guess as to what the beam looked like, and that guess was wrong, and so we had to iterate and update our MU. We don't have to do that for this problem, even if we did have to compute MU. So I'll put MU here, but I'll say not necessary for known cross-sections. I'm not going to go through that on this example because, like I said, I mean, we've already done it once. I'll go ahead and spoiler alert, this does work. You should go through this and check, but you really should. Not only does it work, this is a pretty efficient beam. So. Any questions? All right. If you're okay with that, let's talk about slabs. Okay? Understanding how the design of a beam with a known cross-section works is pretty important to understanding how slab design works. Now, I'm saying slab design, but the slide says one-way slab design. Well, what's the difference between one-way slab design? Is there two-way slab design? Yeah, there is two-way slab design. Is there six-way slab design? No, there's not. All right, so what's going on with one-way slab design? Okay, so here's a typical floor system, right? You got beams, you got columns, you got girders between that, and then you have the slab. And so first off, what I want to try and do is try and tie this, in a bow in terms of, ultimately what we're trying to arrive at throughout this entire process is how to design the floor system. So the floor system is basically going to comprise of beams and slabs, okay? Now, let's talk about the slabs. I propose that there's really two different ways that slabs are going to behave in a general structure, okay? One way and two-way. So what's going on? What's the difference? What's the difference between a one-way slab and a two-way slab? Well, the difference between those two elements is how we assume that they bend. A one-way slab is assumed to bend one way. In other words, it's only assumed to bend in this direction. Whereas a two-way slab, you can sort of think of a two-way slab as almost kind of like a square trampoline. Like the slab is kind of like the stretched fabric. And so imagine if I had a trampoline, right, and I loaded it down with weight. It wouldn't just bend like a notebook. Like if I took the notebook and fold like that, it wouldn't bend like that. It would bend this way, and it sort of bend two-dimensionally, right? Like you can kind of imagine if I had a trampoline and I just put a big like weight on it, the whole thing would sort of deflect in both directions. Does that make sense? That's the difference between a one-way slab and a two-way slab. Okay? Go ahead and tell you, two-way slab design is tough. Okay? It is very difficult. But it's well beyond the scope of this class. There are some advantages to two-way slab design. The main advantage to two-way slab design is that the resulting floor systems tend to be a little thinner, okay, which can make a really big deal. I'm going to give you a very specific case study, okay? How many of you have ever been to Washington, D.C.? Okay, if you've been to Washington, D.C., you might not realize this, the first time you're there, but I'd like you to take a look at the skyline one time when you're in Washington, D.C. There is a city ordinance that states if you're going to build a structure in Washington, D.C., it cannot be taller than what? The Washington Monument. Take a look at the skyline. The Washington Monument's the tallest structure in the city. Okay? Now here's the thing. All right? Let's say that I'm a developer and I'd like to build a skyscraper in Washington, D.C., and I'd like to have as much floor space as possible so I can take that floor and sell it at X number of dollars per square foot or rent it out at X number of dollars per square foot, right? So if I'm the developer, I'd like the most square footage possible, right? Okay, now here's the thing. If you use a one-way slab system versus a two-way slab system, the two-way slab system is a little thinner. But it's not like it's, 2 feet thinner. You're usually saving a few inches. But take that few inches and extend it over like 30 or 40 stories, okay? Think about that. Every 30 stories or 40 stories, what do you think you get? You get another story for free because that 4 inches is going to add up over the height of the building. So think if I'm a developer, that's a whole nother story of square footage that I can go sell somebody and make some money on, right? So in Washington, D.C., two-way flat slab construction is how they build just about every tall structure in D.C. because they want to make money, So that's a very common construction practice. Two-way slabs can come in a variety of formats. They can be just flat slab. A common instance is a waffle slab. So a waffle slab, it basically, if you look above it, it looks like a waffle, so it's flat. But there are ribs sticking out that go this way and this way to reinforce the strength of the slab. They use that on systems where the floor loads are a little higher. One actually very local example is Drinko. If you look at the floor slabs in Drinko, they're two-way waffle slabs. If you were ever like in the guts of Drinko, because I've been on some of the roof installations of Drinko, and if you look, it's all waffle slab. And because what do they got in Drinko? They've got book stacks that are 150 pounds per square foot, so it's a lot heavier. So just a piece of trivia. Now, in most normal, everyday reinforced concrete construction, though, you're going to use one-way slabs just about any day of the week. So I want to go through one-way slab design with you. Like I said, if you understand how a known cross-section design works, then you understand how a one-way slab works. So here's sort of how a one-way slab works. So I have an image here of a one-way slab, and let's assume that slab this way, sort of this way, and this way, let's assume it goes on forever, okay? So the way that we design a one-way slab is we typically cut out a little strip of that slab. Now it really doesn't matter how wide the strip is, it could be anything. What we do is we take a 1-foot strip or a 12-inch strip. And what we do is we say, okay, how much reinforcement do you need inside that little 1-foot strip? And so we determine that, and then whatever reinforcement we get in that 1-foot strip, we just repeat it everywhere, okay? And that's how we design the slab. So a couple things that I want to sort of point out about slab design that's a little different. Okay, first off, when we determine our reinforcement, we're not determining like an AS, just like this is how many square inches of steel we need. It's how many square inches of steel we need per foot of slab. So we do that, we determine how much steel we need in this foot, and then we repeat it. So there's actually a different design aid that we use for slab design, and I'll print off copies of that and bring it on Monday. There's copies on Blackboard as well, but I'll have hard copies for you on Monday. And so that's one point worth mentioning. Another point worth mentioning is the fact that there's actually two different layers of steel, okay? So here's sort of, I want to sort of draw this out. So here's the beam. I'm going to try and do my best to sort of draw it over here. So here's the slab beam that we're considering. So this is me sort of cutting out this chunk and sort of setting it over here, okay? There's actually two different layers of steel that we need to put in this slab, okay? Now there's the main steel, the main reinforcing steel. That's going to go along the direction of bending. So there's going to be main bars, let's say, that sort of go this way. Okay, that's the main steel. Okay. However, there's also going to be another layer or another series of steel reinforcements that are going to go this way. Okay. So we have different steel patterns that we have to design. So we've got what we call the main steel, which is going along the direction of bending. But then we have this other layer that's called the temperature steel. Okay. Why do we have this this additional layer of steel? Well, one of the differences between beams and slabs, spoiler alert, is that slabs are thin. They're much thinner than these super deep, super massive reinforced concrete beams. So as a result, when you have temperature changes in a building, what do you think is really going to be more susceptible to cracking? The beams or the slabs? Slabs are going to be what's more susceptible to cracking. So we end up including an extra layer of steel called temperature steel that's supposed to prevent, that's meant to prevent that cracking under thermal effects. And other things like creep and shrinkage and all sorts of things. A couple things, another thing, unless otherwise noted, the cover for a slab is 3/4 of an inch, so that's from the bottom up. And so a typical estimation that you use for slabs, instead of saying the height is D plus 3 inches, we say the height is D plus 1 inch because the dimensions are a lot smaller. One other point. Slabs, and when it comes to temperature reinforcement, we're not going to use this in here because we're going to try and keep it simple, but temperature reinforcement is a prime candidate in slab design for the use of welded wire fabric. Instead of using these super huge rebars, maybe you can just use some welded wire fabric. In the end, though, you're still going to have steel this way and steel this way, so you just got to be cognizant of what you're doing. The nice thing also about slabs is that the thickness of that slab is pretty easy to determine because we're actually going to use this same guide that we did before. Remember how we used this guide in order to determine the minimum height of a beam for design purposes? So if we had a beam that was, let's say, 22 feet long, we determine the minimum height as L/16. Well, we can do the same thing for slabs if you have a simply supported beam or a simply supported slab. Just instead, because it's a slab, the height limit is a little different. It's not L/16, it's L/20. Everybody good? I do have one final point to mention, and that's this. Okay, what is this dimension right here? If you were to try and tell me what that dimension is, like what would you call it? Not the number, like what would you call it? Okay. This is what I'm going to do. Okay. You are correct that it's the span length of the slab. But what else is it? What's that? Width of what? I think you're thinking too in-depth about it. What I'm saying is that the span length of the slab is the same thing as the beam spacing. So if you have a floor system and you have like beams that are 30 foot long and the beams are spaced every 10 feet, well, the span length of the beams is 30 feet, but the span length for the slab is 10 feet. Does that make sense? Because it's from beam to beam. What do you mean? Well, yeah. Well, I guess let me go back a little bit. What I'm sort of talking about is, so that's slide 137. I'm sort of talking about this. So if you have a floor system like this, right? And so let's say we're talking about the slab, you know, right here. The beam is right here. So the beam length is 30 feet long, right? But the slab, goes from beam to beam, right? So what is going on here? So the slab span is 10 feet. Does that make sense? What's that? Yeah. Yeah, see, sort of, I'm thinking of something like this, like the slab goes from here to here, even though the beam goes from here, like all the way to where it sits on the other end. Make sense? All right. There we go.
So if you were to increase the span length or whatever, that would have become a two-way slab if it was more like this.
That's a good question.
I guess, is that like the difference? It's just the width?
That's a good question. So here's sort of how I'll answer it. So so what you're saying is, if the span length or if the girder spacing gets larger, does it become a two-way slab? In actuality, it might. I mean, if you spaced your beams out to where it was square, then I would say like if we're talking about the physics, if I looked at it, yeah, it's probably behaving like a two-way slab. What I'm talking about here, though, is not really so much how it actually behaves, more how we assume it behaves from a design standpoint. See, let me say it like this. Take this system right here. I propose that this system is going to primarily behave like a one-way slab. But am I saying that there's zero bending moment going this way as well? No, I'm not. The question is not how it actually behaves. The question is how we assume it behaves. I am assuming it behaves like a one-way slab. Okay, now there's a couple reasons for that. One, it makes the design a whole lot easier. Two, it does satisfy the principles of statics. Like I can use tributary widths and span lengths and whatnot to determine loads, and I'm not violating the principles of statics. And so it's a design method that's easy to analyze and easy to design. Now, in fairness, the downside is that I may be over-designing those slabs a little bit. That if I were to take into account the fact that it is really accepting some of that load in a two-way bending action, then I might be able to design a slab that's a bit thinner. That's true. But in order to do that, that math gets a lot more complicated very, very quickly. So two-way slab design, like if we were being real, two-way slab design is something we would discuss after we had gone through an entire reinforced concrete design course and you had experience in moment shears and deflections and all these other things. It's like, okay, now we can talk about two-way slab design. We're just not there yet. So that's reasonable. So if you took like a reinforced concrete 2 or a grad level concrete design class, you'd be doing two-way slab design. So easy. Any questions? So, excuse me. So once you've determined this, the design procedure for a one-way slab, look at this. It's almost like copy and paste what I just did for known cross-section design. So if I have to design a slab, it's pretty much the exact same procedure as a known cross-section. Why is it a known cross-section? Even if I don't have a clue what the slab looks like, well, I know that the width of the slab is 12 inches because I'm assuming a 12-inch strip. And as for the height, well, I can take the height from here, and that ends up actually being the height that we use. So I take this height, I'll take the depth of something like the height minus 1 inch, and bam, there's my beam. Now the cross-section's known. And if the cross-section's known, assume phi equals 0.9, go through this process, and bam. The only other thing that I think is worth mentioning before we call it for today, because I don't really want to broach into a massive example, but because you're talking about slabs and because you're talking about a 12-inch strip of a slab, the actual moments that you're dealing with are a lot smaller. So it's possible in slab design. So we've been dealing with moments that are what, like 200-foot kips, 300-foot kips. You might be in slab mode and you might have like 20-foot kips or 10-foot kips because they're just much smaller elements. They're just not seeing as much load. So I don't want you to be in design mode and go, what the heck, these moments are too small. They don't make any sense. That's normal. That's okay. All right? Everybody good? So if you're okay with that, what we're going to do is we're going to go through a design example next time. The only thing that'll be different with this example and what we just did is we'll have a different design aid and we will have to design 2 different layers of steel. Fortunately, the temperature reinforcement is really easy to design because it's not like we have to go through a process. ACI specifies a minimum or a temperature steel requirement. It's just 0.0018 BH. And so all we have to do is just pick a steel pattern that follows along with that and we're good. So temperature steel is really, really easy to design. And this is going to be our example. We're going to have a one-way slab. I say the span length of the slab is 10 feet, but really I'm talking about the girder spacing, the space between the beams. So it's going to be a 10-foot slab. We're going to use 4 KSI concrete, 60 KSI steel. It's going to have a 200 pounds per square foot live load. So this is a really heavy floor load. I mean, normally we're looking at something, like 80 or 60 or something like this. This is really heavy. This is beyond library loads. And the only dead load is the slab self-weight. So this is going to be a little bit comprehensive, but we'll start this next time. So on Monday. Sound good? Don't worry. We'll do it start to finish, and then that'll be exam 1. After that, we'll get into some beams that are a little more complicated. So flanged sections, things like a T-beam and a reinforced concrete, like a doubly reinforced concrete beam. So that's all I got. I'll see you. These folks are excited about steel design. I know the guy teaching the class is a jerk, so.